Okay, then let's follow the order. You made 6, right?
Yes.
Okay, yeah, no problem.
Great. Good morning, everyone. My name is Kelvin. I am present to our work entitled Quarter Car Suspension Optimization using the S2P algorithm. Our study focus on enhancing ride comfort and handling performance by tuning suspension parameter through a constraint optimization approach. This is our flowchart illustrating the optimization process. We begin by defining the optimization objective. Next, we construct the dynamic model of the quarter car and apply various road input profiles. We then simulate the initial system response and evaluate the cost function using multiple ride comfort and handling performance metrics. Subsequently, we use S2P algorithm via fmin_conv to perform constraint optimization. If convergence is not achieved, the parameters are adjusted and the process is retried. Once convergence is converted, the system is resimulated with the optimized value for comparison, and the results are plotted and set. This slide shows the mathematical model of our quarter car system. It includes bubbles, sprung and unsprung masses, suspension spring and damper, and tire stiffness. The road input acts on the unsprung mass, and the equation describes the vertical dynamic of both masses. Tire damping is neglected due to its relatively small influence. The model provides a foundation for analyzing how variation in road profile and suspension parameter affects ride dynamics. Our objective function is defined as a weighting sum of 5 performance indices: ride comfort, traction, suspension, deflection, energy efficiency, and pH balance. Each term is integrated over time to capture the dynamic behavior of the system, including acceleration velocity, suspension travel, and pitch rate. The weighting factor W1 to W5 can be adjusted based on desired priorities. In our case, we optimize 2 key parameters: the suspension stiffness Ks, the damping coefficient Bs, both bounding within realistic physical constraints. Next, we evaluate the system using a predefined set of weights and test its response to various load profiles. We test the current configuration using a small parabolic bound profile as the load input. The left plot shows the load displacement input, while the right plots compare the vehicle's vertical displacement and acceleration before and after optimization. As observed, the optimized suspension parameter result in noticeable reduction in peak displacement and acceleration. The body acceleration center factor indicating improved ride comfort. Although the improvement is moderate, the results confirm that the S2P-based optimization efficiency minimizes vertical dynamic response. Under the given constraint, these results validate the baseline setup and establish a foundation for more advanced control or modeling extension. Here we evaluate the same optimized suspension under a more challenging multi-bump load profile. The left plot shows the pre-bump input, while the right plot compares the vertical displacement and acceleration response. As shown, the optimized design consistently reduces bump displacement, peaks, and acceleration. Foundation across bumps. This indicates better vibration control and improved ride comfort under repeat distributions. In this case, we test the suspension under a more realistic, irregular road profile that follows a Class B surface standard. The left plot shows the stockage ride improved while the right plot compares body displacement and acceleration. The optimized design still achieves reduced vibration and smooth response over time. However, since we only tune two parameters spring stiff KS and damping BS, the overall improvement remains modest. This suggests that further gains may require a more advanced model or additional control variables. In light of this limitation, our future work will focus on extending the system to a half-car or full-vehicle model. The half-car model incorporates pitch dynamics and introduces additional variables, such as front and rear suspension parameters, enabling a more realistic and controllable design space. This extension and to better capture the coupled vertical and angular motion of the vehicle body, ultimately improving optimization outcomes. The dynamic equation for the half-car model are shown here. They describe the vertical motion of the front and rear wheel masses, the chassis body, and the rotation pitch of the vehicle. This equation incorporates the interaction between suspension force and vehicle geometry, including the lever arm B1 and B2. Although this model introduces increased complexity, it enables a more comprehensive analysis and control of ride quality and overall vehicle dynamics. To evaluate the performance of the half-car model, we define 5 criteria: vertical acceleration of the chassis, velocity of the unsprung masses, suspension deflation, pitch angle, and pitch jerk. These variables correspond to different aspects of ride comfort and handling. Minimize these indicators serves as the basis for our next stage of optimization. This slide shows the key constraints in our suspension optimization. We limit the suspension travel to 8 cm to prevent mechanical failure, and we constrain the pitch angle to within 5 degrees to ensure stability and ride comfort. These constraints keep the design both realistic and safe. Finally, here are the key references regarding our model design and optimization strategy. These include foundation work on suspension design, vehicle dynamics, and the SUV algorithm. Thank you.
Okay, it's great. One question, can you go to the spring and temporal system? Any figure? One of the figure of your spring and temporal. Yeah. So, in this particular one, are you only optimizing KS and BS? The variable. Because in your next slide, next page, page 4, I think your variable is only KS and KS and BS.
Yeah.
Right? If you go back, how about KT and BT? So KT and BT represent the tire?
Yes.
So it doesn't change?
Yes.
I see. How about the page 8? Page 8. So in this one, do you optimize K1, K2 at the same time? Can they be different? K1 and K2?
Yes, it's different.
Different, okay. But KT1, KT2, they are types, so they don't change.
Yes.
Okay, got it. It's a pretty good work. I think you can go to, for example, page 5. Now you have, on the left upper corner, you have a choice of your weighting coefficient. I recommend you to try different combinations. Yeah, because you are working on multi-objective optimization. So different combinations of weights represent different kinds of preference. They are all correct answers. And also for, usually the sum of the weights equals to 1. But that's fine. It doesn't change the result. It's just it's easier for people to get a sense what's the percentage of importance of one factor. If one is 0.2, the other one is 0.1, okay, this is 20% of importance, this is 10%. Total is 100%. But now the sum of your weights is now 1. So it's people need to do some calculation in their mind to realize which one is how much percent important. Okay. So I recommend you to change the value so the sum equals to 1. And in your page 5, 6, 7, you show 3 different kinds of row profile. I think it's very good. But from here you can already see for different profile, different weight preference, you have different results. So there is no overall best result. So, but in reality, when you drive a car, your car truly needs to go to different kinds of road conditions, and sometimes you may want to speed up. That's one for one preference. Sometimes you want to go up to a hill. That's a different preference. So in reality, for a car, you need multiple functions and also phase multiple road profile. So from here, you can already see there are so many choices. So I recommend you to figure out what you can do next. So maybe at least at the end, you can give an overall solution. Maybe there's a kind of research people said it's like a random row condition. But how can you be sure it's random enough? So there are people try. Sometimes people will run this kind of analysis with a lot of row conditions, and they want to find the overall best. So maybe it's very good in one condition, but bad in others. So there must be, so for each row condition, you need to give a score. So let's say you try 10 different random row conditions. You have 10 scores. So the overall score is the overall objective function. So the overall best is the best, because that's the one that can at least be okay in all conditions. It may not be the overall best, but it scores okay everywhere. Okay, so that's another mindset. So I think it's pretty good. And also when you present, like in this particular one, I would be interested in how much improvement the optimization achieved for each objective, because you have 5 objective functions. You have an initial guess. So once you reach the optimum, each initial objective function will be improved to a certain lower level. And each one of them will improve in a different way, because your weighting coefficient is not the same. So it would be a good idea to show how each objective function improves based on your current setting, so that you can let people see, because of your weighting coefficient is being defined this way, so one of the terms improves so much. So then you know with this optimal setting, this suspension system behaves in a certain way. So actually, there's a lot to analyze. Okay, good work. Next group.
Hello everyone, we're Group Floor and I'm Zhang Jie. My team member is Wang Yanhong and our topic of our project is optimization parameters for helical gear design. And then this is our outline. And we focus on helical gears, which are smoother and quieter than spur gears due to better contact. And since their geometry is more complex, and we use the GA algorithm to optimize the key design parameters and improve their performance. And here is the contact ratio, and the contact ratio is a key indicator of the gear performance. So a higher contact ratio means the gear makes lower noise and less vibration and smoother operation. So we use a transfer contact ratio formula like shown here. So we have to maximize the contact ratio, and in our optimization, we have to minimize the negative things about the contact ratio. And then these are our fixed design conditions, and the gear ratio is 3, and the center distance is 150, and the face width is 30, and the torque is 100. And the tolerance allows the flexibility in optimization, and the face width and the torque are reserved for future stress evaluations. And here are our design variables. And in this table, we use these 5 parameters for our design variables. The first is model, and the number of teeth, the helix angle, and the pressure angle, and then the profile shift coefficients. So we optimize 5 key variables here, and these variables affect gear geometry and the contact ratio. So this is our result, and then we can see that here is our contact ratio is 2.16, and this means it performs very well. And then the actual center distance is 149. So it's very close to 150. So here are our follow-up. We will check the blending and contact stress to ensure the gear meets stress requirements, and we also choose the material and apply stress formulas. Thank you.
Okay. Can you go back to the result? So your module N is one of the variables, and the optimal value is 1.53.
Yes.
Is it available in the category? The manufacturer category? You should be not available. So if you check gear design book, the modules are only given numbers.
Yeah.
Because they have design tools to manufacture the gears in certain shapes. in different modules. So you cannot design a gear with some other numbers.
Oh.
It will become some gear profile that cannot be manufactured easily. So it's okay to do this, but it's not fitting the manufacturer's book. So you can use this optimal and find the closest value. But let's say 1.5. There are two closest numbers. One is smaller, one is larger. So I think in your program, you need to have a list of available numbers. So whenever you find a solution, okay, now test the available ones next to the optimal. So the small, one step, tiny, slightly smaller one, and slightly larger. The reason why I want you to try both is because maybe one of it will violate your constraint. Do you have any constraint in the problem?
Oh, yes. Yeah.
Yeah. So, no, which one is constraint? Which one?
Yes.
These are the
Yeah,
constraints.
these are
Okay,
constraints.
okay. Those are variable constraints. You actually have a lot of constraints because you need to satisfy the gear design equations. There are a lot of inequalities. In your optimization, did you apply those equality equations? Okay, go back to your identity function. Go back. So,
Okay.
so you're maximizing this,
Yes.
right? Do you think all the values that you get at the end still satisfy all the gear design equations? Gear design equations, they are equalities, equal sign, a lot of them. How are you sure they still satisfy? OK， 中文好了，受不了。那个齿轮设计不是有很多等式的公式吗？你的最佳化里面有那些公式吗？
我把它记不起，就是它是用那5个，
所以我刚刚讲的真的听不懂。
我刚刚在想要怎么讲。
I go back to English. You can answer in Chinese. That's fine. I need to be professional. I have to do this. So yeah. So you need to mention what are all the equations in your optimization. Can you tell me what you have done? 你可以说中文吗？
就是把他们，就是刚刚那边有用到的电子这边都有拍过，他就把它塞进去。
Okay. Your answer is not very clear. You need to show what has been included in the problem, right? If you did not show it in your presentation, it's not very clear. So how many equations are there in your optimization? Do you know? 20? So all the equations are there. Okay. Which optimizer did you use? Whoever knows can answer in Chinese, please. Speed up. Which optimizer did you use? optimizer? Which tool? Which method? Which software? 你们用什么最佳化方法啦？拜托啦。Okay, so it never mentioned.
We have say in
No, you need to show whatever, like chromosome. I told you this is an optimization course.
Yeah.
Okay, what's your chromosome design? How did you design it? Okay, what did you do for the selection, mutation, and whatever? Or did you just use MATLAB GA and type GA? Did you rely on that, or did you write it on your own? So you need to emphasize what has been done about GA.
Okay.
And for the GA, okay, then did you do feasibility check? So when you do feasibility check, did you check all the equations? So when you see a design that is not feasible, what did you do? And since you have available module numbers, let's say 20 of them, you can already use them in GA. So like for GA, you can have for every bit, like three bits. You can say 0, 0, 0 represent the first module, 0, 0, 1 second module, 0, 1, 0 third module. So you will not deliver numbers that is not available, right? So there are many things that you can work on. Did you write your own GA code?
We use a tool on that.
That's why. Because when you rely on the tool, you have no control of what you want to do. So GA is a very simple program. I recommend you to write it on your own. It's very simple, very easy. And also there's available code in my lectures, right? Very easy to use. So I recommend you to pay attention to how to use GA. Okay? Yeah, so if you have questions, let me know before the final week. Okay? Okay, next group.
Test. Hello everyone, group 3, I'm Andrew and my partner is Jerry. Our subject title is Stimulating Path Optimization of an Autonomous Mobile Robot in a Program Working Environment. Here is our outline. We will introduce our experimental and do the path finding testing for you guys, and we also show the preliminary result. And finally, we will talk about our future work. Here is our experimental introduction. Our framework evaluates obstacle avoidance using the A-star algorithm in environments with static and dynamic obstacles. We first assess pathfinding efficiency by tracking iteration, then assign various tasks to validate system performance. Here is our A-star algorithm pathfinding testing. We conduct our experiments in Python using Yan's open source code to test A-star pathfinding with movements initially limited to horizontal and vertical direction. The pathfinding testing we refer to research by the LaConte teams and adopt their risk-wise path evaluation formula. The F function equal to G function, H function, and lambda plus R function. Here, F function is total cost estimate of the path. The G function is the no cost. The H function is the estimate cost. The R function is risk factor. The lambda is the risk weight. Here, I'm sorry about today's report. I forgot to put on the constraint. I will add the constraint at the final report. Our constraint is to estimate the F function total cost estimate of the pass. Here is our dynamic obstacle avoidance task for a single robot. This is version 1. We limit the robot only can go the straight line, but that's meant the avoidance performance is not good. So we do the version 2 to do dynamic obstacle avoidance task also for a single robot. Version 2, that's the robot can walk a curved path. This avoidance dynamic obstacle performance is better than the version 1. And here is the single robot's task from flow chart. The start we initialize the environments, then we use A-star algorithm to generate the path to target. And if the robot reaches a goal, we will assign new random targets for new tasks for the robot. And if not, then we will detect the dynamic obstacle. If the dynamic obstacle exists in the path, then the code will adjust the robot speed and direction until it's moved toward the target.
Okay. In our second test, 2 robots are placed at different starting positions. They first navigate to a meeting point, then proceed together toward the next target, repeating this cycle as their working pattern. The task flow for 2 robots is as follows. Set up the environment. Use the A-star algorithm to optimize the initial path for each robot. Each robot will have its own loop. If one robot reaches the target first, it will wait for the other to arrive. While moving, if a dynamic obstacle is encountered, the robot will adjust and change its path to avoid it. Further detail will be introduced on the next slide. As mentioned earlier, each robot operates within its own loop. If only one robot reaches the target, the loop continues. The loop only terminates when both robots have arrived at the target. A new target is then assigned and the robot begins a new cycle. We have successfully created a dynamic obstacle avoidance system using the A-star algorithm and test its effectiveness with 2 types of tests. In the coming weeks, we will refer to the secretary bird optimization algorithm proposed by UFA to develop a mathematical model for dynamic obstacle avoidance and path optimization. Here is our reference, and thank you for your attention.
So can you go to the reference? One page up? Or say here. So which one is the one that you got some coding? Which reference provides some coding?
Reference 3.
Okay. So what did you do based on reference 3?
Oh, based on reference 3, we can watch the result. The detect circle range is our.
What's your contribution
Our
on optimization?
Our contribution is to
Download the reference 3.
Oh no, we adjust the constraint and do.
Okay, what did you do? What did you adjust?
We adjust the detect distance and the danger zone.
So some parameter change.
Yeah.
So the method-wise is the same, right?
Not same method. We do adjust on the flow chart. We change the file. Our file is different to the
Your
reference.
process flow is different.
Yes.
What is different?
Oh, let me show for here is the left picture is the Yen's result. He just do the static dynamic optimization, and our project is do dynamic obstacle avoidance. So we add the floor for the dynamic.
So this one is linear. This
Oh,
is what the right hand side.
The right hand side is our
By yourself.
by ourselves. The left side is by the reference tree.
Since you got something from the literature,
Yes.
so it's very hard for me to judge what you have done. So how do we judge?
Like this, we add a new robot.
So in the reference, there's no moving object.
Yeah, in the reference there, no moving object.
Okay.
In our program, we add the moving project, and we can adjust the danger zone and the detect range and the speed.
So whenever
Yeah.
a moving object is get into the danger zone, what do you do?
And robot will.
Robot will adjust its
But
speed.
I mean, concept-wise, it makes sense, but there's no math, it's hard to tell why is it working. And in one of the animations, sometimes when you are moving toward the goal and you show a circle, maybe that's like a danger zone, and some pink box is following behind you.
Pink box is
Is an object, right? Moving object.
yes.
So obviously the pink object is behind you inside the danger zone. But I don't see any change of your trajectory.
Because we said when pink box in front of the robot, we will slow and.
Well, your animation doesn't show what is in front. How do you define so-called front side and back side, left side or right side?
We to design we
Or
use
45 degree, 30 degree. How do you define?
we use two vector when
Okay, so it was never explained.
yes. So we need to
Yeah, so if that's your contribution, explain that.
okay.
If you only show a fancy animation, it's great,
Okay.
but it's hard to believe. If it came from someone's paper or some code written by others, then you cannot say it's your credit. But if it's something you have done, it's your credit. You need to highlight it. Okay, this is what we decided to work on. Okay, so emphasize those. Okay, so if most of the new stuff is made by you, it's really good stuff. Okay, pretty good. Maybe you can try 10 cars, 50 moving objects. I mean, if the algorithm works, it works, right? No matter how many cars you have.
We want to try more target and more robot to
Yeah, 10 cars.
okay.
10 cars, 50 obstacles. So eventually it's like people moving in a crowd, right? And then they eventually get to their goal point. Yeah. And that's a little extreme case, right? And this is like a more usual case. And you can highlight whatever you have done. For example, focusing on moving objects in a front detecting zone, do you focus on the 30 degree or 45 degree or 90 degree or all the way 360 everywhere? So those are parameters that you can choose, and you can then do some tests with different settings and see the results. And for the results, you can, because it's kind of random, you may need to run the code 10 times and then do an average and show the average cost for the final trajectory. So you will have some kind of performance. And you can also show average or the minimum distance you get between the robot and the moving person. Because that's the riskiest, most risky condition that you met along the way, right? So maybe there are some setting allows you to stay a little bit further from the moving object. So this kind of setting is safer. Maybe the safer setting takes longer time to get to the goal. And if I become more risky, I can get to the goal faster, but maybe the moving object will get so close to next to me. Not bumping, but so close. And maybe if I tune the parameter to a little bit more extreme, I may hit the moving person, right? So yeah, then you can focus on what you develop, emphasize what is yours. When something is from the A star is nothing new, that's fine, that's just a tool, but you have your own strategy. And then your tests, various kinds of tests to show your strategy works. Then this is a good project. Okay, nice.
What about if two cars are very close together and one car acts as an obstacle for the other one? If there are two multiple cars in the same path and one car acts as a dynamic obstacle for the other one, how it is?
So yeah, how about two cars hitting each other?
Like in multiple cars, there is an issue of this.
So I mean, it's a good point. Maybe you can also consider all the robots as a space. So actually, the cars cannot stay at the same position. Right now, I think you don't treat cars as obstacles. Yes. So they are allowed to stay at the same point. Okay, next group.
Good morning, everyone. We are here for reporting the progress of our project Smart Garden Watering System. Me as Titi Andini and my friend is John. I will pass the introduction for this. And our research focus on optimizing the movement of mobile watering robot in smart garden. So, for the goals and the objective is to minimize the total travel distance of the mobile watering robot and to ensure that every plant in the garden is visited and watered, and also for the avoid redundant heads and improve energy efficiency.
First, we input the green map into the system. In the map, there are selected obstacles and 10 points in total, which include 9 target points represent plans, and on 1 initial point represents the robot starting position. Next, we apply the extra algorithm to calculate the set path between any 2 points. This ensures that the routes between points avoid obstacles. After finding all possible set paths between 2 points, we count the path lengths of each route and build the distance matrix. The established visiting sequence rules. Then we define the visiting rule based on the traveling salesman problem. The robot must start from the initial position with all 9 target points and finally return to the initial position. GA genetic algorithm to research for the optimal visiting sequence. We apply a genetic algorithm to solve the optimization problem. Optimal route once the optimal visiting sequence is obtained. We can combine the previous calculated extra path between each pair of points to generate a complete and optimal route for the robot. Finally, the system will output the total travel distance and draw the complete path map for the robot to follow. We use a generic algorithm to help the robot find the shortest path to visit all plans location. First, we turn each visiting order into a chromosome, where each plan's location is a journey. Then we randomly create a group of different routes as the initial population. Each route is scored based on its total travel distance. The shorter the distance, the higher the score. The best score routes are selected to reproduce through crossover and mutation, creating new routes. This process repeats with each generation improving over time. In the end, we get an optimized shortest route for the robot to follow when visiting all plans. These slides show our current progress using the extra algorithm to calculate the shortest path between any 2 points on a grid map. In this example, we select the start points and the goal points. By applying the extra algorithm, the robot can avoid obstacles and find the shortest available path between these 2 points. The current generated distance is 468.58 pixels. This value will later be used to build a distance matrix, which serves as the foundation for route planning. After computing our pairwise distance between any 2 points, we construct a distance matrix to represent them. Then we apply a genetic algorithm to find the optimal visiting sequence. The goal is to determine the shortest path that starts from the initial point, visit every target location exactly once, and finally return to the starting point. The video on the slide shows an example of the optimized path. In this case, the total journey distance traveled by the robot is 606.01. This result allows us to plan an efficient route for the route, minimizing both travel time and energy consumption in smart garden environment. In the next stage of our project, we plan to explore other optimization algorithms to improve the visiting order and compare their performance with the current method. We also aim to simulate the robust movement in an indoor environment using those tools. The steps. First, we will build a 3D virtual environment that represents the real indoor space. Then we compress this 3D environment into a 2D grid map suitable for path planning. After generating the map, we will calculate the shortest path for the robot. Finally, we will convert the computed path into a series of coordinates that the robot can follow in during simulation and the actual operation. This approach helps ensure the robot can operate accuracy in realized environment.
So the technical focus this current is about the garden is modeled as a 2D coordinate system where each plant is treated as a node, and the robot starts at a base and must visit all nodes with the shortest possible total distance. We are using the traveling salesman problem, and it's using a genetic algorithm. We face the challenges like the increasing complexity for path planning as the number of plants grows, and the need for accurate and precise mapping of plant locations, and transitioning from simulation to real-world environment, and ensuring the system performs reliably. And here the conclusion is about the our project is about the integrate intelligent path optimization to improve gardening efficiency. And it's by using a mobile robot and genetic algorithm-based path planning, we aim to conserve water and energy while providing effective hydration for plants. So our solution demonstrates how automation can offer smart and sustainable gardening practices. So here are the references. Thank you.
Okay. So, can you go back to your GA slide? Okay. Maybe one page earlier. So when you mentioned about the traveling salesman problem, do you mean that you have 9 targets and they have different orders.
Yes.
So basically, your GA handles the order.
Yes.
So about the GA, for each random order, does it run A star?
We use
So next, go to the next page. So here you have a GA. You have random design in your population.
Yes.
Let's say 10 designs.
Yes.
That means you have 10 random orders of 1 to 9.
Yes.
So for these 10 designs, do you run 10 A star?
we have previously to calculate the 2-point distance use A star. So we when the GA algorithm we only use the two.
So A star handles shortest distance between every 2 points.
Yes.
That's what you're about. That's a good idea. So for GA, how many population how many chromosomes you have for each generation? Do you remember? 10, 20, 30?
You say the generation.
Each generation you have random chromosome. How many? Every generation.
10.
10. Okay. Then how many generations? How many iterations did you run?
300.
300. Okay. How fast is the process for 300 iterations?
I don't use the exactly to calculate, but I think it has 5 minutes to 6 minutes.
Okay.
It's 5 seconds to 6 seconds.
5 to 6 seconds.
Yes,
Not minutes.
not.
Okay, it's very fast. Okay. So interesting problem and interesting way of using the tools, but those methods that you use are not new methods. So I try to show you one thing that you can make your problem more interesting. Okay? So please go to one of the pages in your conclusion, maybe the 3D one. Go to the 3D page. Go for it, yeah. This is not necessary because this is still a 2D problem. So don't work on the 3D because it's fake 3D, it's 2D. Okay? Unless you're doing UAVs, that's real 3D. So in this problem, still moving in a 2D plane.
Yes.
So you don't need to work on this. Okay? One page further. Keep going. Okay. So the method-wise, it works. No matter how many plans you put, it works. So you don't need to work on the first one. Not necessary, because adding one more plans, your method won't fail. So that doesn't, it's not necessary for this project. You don't need to try 100 plans. If 10 plans works, 20 plans will work. Okay? Second thing, precise positioning. Not necessary. Let's say the position is like a 1 pixel next to the inaccurate. So what? Right? So it's not necessary for the project. Okay. And real world environment, you don't need to. It's about optimization. So I would recommend you to focus on the problem itself. So in reality, there's one thing you guys forget to think about. And it's very related to the story you mentioned. It's a water planning robot. So at the beginning, the robot carries a full tank of water. So in the first path, it's like 100% water. So it's wasting the most energy. And when it moves to the first spot, 1/9 of the water will be dumped into the plant. So in the second path, it only has 8 out of 9% of the water. So it's energy, saving the energy a little bit, right? The energy consumption is slightly lower. So in that kind of sense, maybe you need to change your formulation a little bit so you will move to the closest early. Because in the earlier path, you require more energy. So if you define energy in your formulation, that's a new concept in your problem. New way to formulate your fitness. You will see different results. And then you can, in your analysis, you can start to test different kinds of preference. Do you want to have faster the better, or energy saving the better? It becomes a multi-objective optimization. So you will have weighted sum formulation. So if you want to have the energy saving plan, the trajectory, definitely you will move to the closest one. And then you will keep on move along the closest one. Definitely. You want the longest individual path to be last one, because that's the most energy saving. At the end is energy saving. Right? And maybe you also want to think about, of course, longer you move, that costs energy. So you need some kind of energy model. Like the energy model depends on how much you move, and also depends on how much weight you carry. So based on that energy model, your formulation will change a little bit. And with different settings, the optimization may give you different results. So that would be something interesting and more related to optimization. Okay? Okay, good. So next group.
We're group 6 and we talked about the optimization of the wafer machine. And I'm Zhongguru and this is my partner Lin Junzhe. And this is our content, and we talk about the problem statements, methodology, the results, and we problem and future work. And these slides show the key number of the Toyota artist. The glass is 1,400 and 750 millimeter. The left wafer is 800 millimeter. The right side is 500 millimeter. For the 4-bar link, the first glass is L1 is 322 plus 5 millimeter, and L2 equal 76 plus 5 millimeter. Link L3 and L4 will be turned by the optimization. And first, this is our problem statements, and we use loop closure equation to find the change of crank angle delta theta. Next, compute the web area to make sure the drive view is clear. And finally, build the objective function that minimizes the web area will keep all link those size their limit. Last time, the teacher suggested that we could change the math, so we went internet to find papers that use BFGS to doing the Whisper machine, and BFGS is quasi Newton math. Newton need second order slope, and it's hard to uncouple because have the Hessian matrix. And BFGS used only first order slope, a bit slower than Newton but much faster than plain gradient search. And so BFGS is maybe good, better than Newton for our question. And this BFGS flow chart sets the first is sets the variable vector x equals 0 and Hessian guessed bk equal one matrix, and computes the gradient slope the smaller linear system to guess the research direction beta k, and do the line search to keep step size alpha k says the sk equal alpha k and beta k, and move the next x. And if the gradient more below the 0.001, we step and record the best link result. Else, we report the step 2.
And then we use the BFGS to find our solution. And for our initial guess, the L3 and L4 is we set at 200 millimeter. And we can see the figure. There's quickly to be coverage in like 12 iteration because for BFGS we give the initial guess for a poor guess. It will be out of a solution, and when the guess is in a correct point, it will be quickly to be coverage. And why it will be like 36 iteration, because the BFGS for the coverage is to check the gradient. So when the gradient is the smallest, it will be stopped. And we found that our L3 is 277.5 millimeter, and L4 is 225.9 millimeter. And for our sweep angle is 108.2 degree. And for our coverage is 80.1%. And after we get the solution, and we use the motion gen to draw our wiper mechanism. But we have some problem about our wiper mechanism. We can see the figure is not look like the normal wiper mechanism. And we think that because BFGS is the local optimization method, and if our initial point gets poorly chosen, and it will converge to a nearby local minima instead of the global optimization. And so we will do next that we will use global search first, and then we use EFGS to find the fine tuning. And after that we get the solution, we will use MATLAB or Python to draw the linkage to make sure the mechanism can be the correct one. And we will make sure the sweep area to be accuracy. Thank you.
Okay, can you go back to, just keep on going back. Keep going. Yeah, okay. Which one is your objective function? Okay, this one. Any constraints?
We didn't put any, but we have the sweep angle constraint.
Like how do we use BFGS?
For now, we use in Python for the package.
You didn't answer my question. BFGS is a gradient-based approach, unconstrained optimization. So if you have constraint, how do you handle the problem? So it's someone wrote a code for you, right?
Yes.
So you didn't know anything. Then you learn nothing.
We will write
No, this is a constraint optimization. If you want to use an unconstrained optimization method, you can formulate a function. And then you can use PFGs. And in your result, you mentioned the result, the design doesn't look like a proper design. Maybe it's because you didn't consider constraint in your Python code. So if you formulate a function, you have minimize objective function plus Lagrangian multiplier and the constraints. It's in the class. It becomes a single objective function problem. It's an unconstrained optimization. Then you can solve it by gradient-based approach, BFGS. And the solution should be able to handle constraint at the same time. So you won't be getting a solution that violates constraint. So if at the end you get a solution that doesn't look like what you want, maybe your formulation is not good enough. Or you can try, like you said, multiple local minimum issue. Then you can try different starting guess, initial guess. See if one of, or maybe you already know a good solution set. Try that one. See if that one gives you a pretty realistic design. Okay? So those are the things you need to pay attention to. And can you go to the iteration part? Yeah. What's your convergence criteria? Convergence criteria. What's the rule for convergence?
For
error smaller than 10 to the power of -6.
Yes.
It's very weird to see this kind of change.
Yes.
Don't you think?
It was.
Usually gradient base is more like a smooth change.
Yes.
And if you have no change at so many iterations, then how come it doesn't converge? So, for example, if you look at iteration 20 and 21, maybe 20 and 21 are so close, you should get convergence. So you need to, that's why I always ask students not to rely on tools. If you rely on tools, you have no control, you don't know what has been done. This is an optimization optimization course. I teach optimization and I show you example codes. this is definitely something you can do it by yourself. Yeah, so if you have no control of the math, then you are just showing something you have no idea what happened. Then you didn't learn enough. Okay, so I would recommend you, if you still like the code that you download, that's fine, but at least you need to know what happened. Okay, and maybe you can also see the trend of all the function values. Object function values, constraint values, see what happened. Or also compare with Newton's method or other gradient-based approach. This is just a gradient-based approach that I didn't introduce in the class. It's very similar to conjugate gradient, but even more advanced than conjugate gradient. And we have learned about these gradient-based approach. You can try to compare with them and see the difference between each trait. Don't rely on tools. Okay, thank you. Next group.
Hello, Professor. Hello, everyone. This is Ben, and here my partner Sam. And our objective is hinge board layout optimization for laptop vibration issue. In the our content will include the recap and progression, methodology, and preliminary results and schedule. A little recap to our project. We want to optimize the laptop LCD's vibration performance by only changing the board layout design. And the optimization objective will be minimize the vibration amplitude of the LCD model. And the methodology, right now, we've been adjusted to using finite element analysis to conduct DOE, then regression experimental data to the stiffness model, and then apply a single objective linear programming for optimization. So we've been model a simplified laptop LCD, which we remove the hinge torque part and change it as a rigid body. And as you can see, it's almost like a L-shaped plate. And then we use two different board layout parameter set. And then we're using ANSYS to conduct FEA model and link the model analysis result to the transient structure simulation. And we're using the material of aluminum alloy. And this is its material parameters. And we found out 6 models, and this should be a draft, but it's moving a little slow. But the model 1 is right now, from the practical observation, is the most likely the one deformation we are looking for. So, and then it happens at the low frequency, which is 84.344 Hertz. So this is most likely approach to our performance. So we will use model 1 to link to our next transient structure analysis, and we use these two parameter set, and this is its max amplitude. And so we found out that indeed the board layout does impact the stiffness of the LC model. So therefore, we will doing some more DOE to obtain the regression model and then do the optimization.
So in mathematics, we use in DOE, we use the L9 orthogonal area to efficiently explore different board layout combinations. So for each configuration, we perform finite element analysis to extract the vibration response data, include displacement and dampness. So next, in the regression modeling stage, we analyze the FEA result to establish regression models. This model helps us understand how both position affect system stiffness and vibration performance. So next, we move to the upper approach. We use the linear programming or sequential linear programming. This measure helps us find the optimal box layout that minimize the LCD vibration without altering other design parameters. And these are our schedules. Thank you.
Okay, so can you go back? Okay, so you have 6 models. Are you going to run more, or that's it?
Right now, we found the model 1 is the most likely suit for the relating situation. So we will stay in this 6 model. We will do no more model analysis.
So those 6 models came from your DOE?
Came from our
But your DOE is L9.
The DOE is DOE hasn't been conducted.
So I'm very confused. You mentioned you are going to run, you ran 6 finite element models. And I don't know why you pick up 1 out of 6. What does it mean? And then you later on are going to do DOE. But after DOE, are you going to run more simulations?
Okay, so
It's very confusing.
okay, so let me expand a little bit. So this 6 model, excited by different hertz, is on this is what happened on this K model.
When you say this and point, I cannot see it. I don't know.
Oh, okay.
I don't know what you mean.
I'm sorry.
You can come up if you want.
Yeah. So this 6 model right here, as you can see in the red or yellow, the light color is where the amplitude is the most. So these 6 models all happens in the same our CAD model. Yeah, and then these 6 happen in different hertz. So our goal is to simulate the real laptop after the real laptop
So
LCD.
maybe let me try to describe what I know.
Yeah.
I guess you ran the nodal analysis, right? Nodal analysis.
Yes.
Okay. Then each one of them represent different nodal analysis at different frequency.
Yeah, different behavior. Yes.
You only care about the first one.
Yes. I'm sorry.
Because the rest are just higher frequency.
Yes. We only care about the first model.
The one with the lowest frequency.
Yes.
Okay. So.
And then based on this model, we will do transient structure analysis.
But later on, you are going to do DOE, so that means your geometry will change a little bit.
Yes, only change the position of the.
So every time you change, you still need to run nodal analysis again. Because the vibrational behavior changed.
In these 2, we have tried. The model doesn't change.
That means you did it wrong.
I did it wrong.
Yeah, because the boundary condition is wrong. The boundary condition is different.
Okay. Yeah.
So I guess you fix the bottom. But in reality, you have different position of both. So I guess the boundary condition is different.
The support is using cylindrical support on the both position.
I mean,
So it's different every time. But the,
I feel like it will be different, right?
but okay.
Okay, let's say it's the same. Then why bother focus on vibrational behavior? Because whenever you change your variable, the vibrational behavior doesn't change. So there's no relation between your variable and your response. There's no point to do optimization.
In behavior, which is model, it doesn't change.
Yeah.
Still the model, there's still a model one.
Oh, you mean the mode doesn't change?
The mode doesn't change,
But
but the
amplitude
response,
change.
yes. the
So that
response
means
change.
for different variable selection, you still need to run answers.
Yes. I need to do that
You
again.
say you don't need to run answers. Now you say you need to. Yeah. So for the DOE, if it's L9,
Yeah.
you still need to run 9 answers model.
Yeah.
Okay.
Yeah.
Yeah, that's my original question.
Okay, I thought you said the model.
No,
Yeah. Okay.
no, the 9 analysis is still nodal analysis,
Mhm.
still multi-modal,
Mhm.
but you only focus on the first mode.
Yes.
And maybe the peak won't be at the same frequency.
Yes. Yes.
So just mention you are focusing on the first node, for the first nodal response,
Okay.
and then you are going to run L9, so 9 different combinations of your variables,
Yes.
and you're going to run 9 answers,
Yes.
and focusing on their first peak.
Yes.
Okay, move forward.
Okay.
So you are going to do regression. What kind of regression?
We haven't decided. We need to see the.
But you are going to do LP, so you can only do linear regression. Otherwise, your objective function is nonlinear,
Right.
right?
Right.
Or you can do, for example, nonlinear regression. So your vibrational response may be nonlinear.
Mhm.
But when you solve it, you are going to solve it by sequential linear programming.
Okay.
So every time when your design point move, you are doing linear approximation of the curve.
Mhm.
Solve LP once,
Mhm.
and then iterate at the next position. You run linear approximation again, and then solve the optimize, and then do this sequentially.
Okay.
So you have nonlinear regression and then SQP.
Mhm.
If you only have linear regression, then just LP.
Mhm.
And you don't need to sequentially do it again because your linear regression will not change.
Mhm.
So I think to make your project more interesting, I recommend you to do, for example, quadratic programming, quadratic regression,
Mhm.
or even higher order. So your function is not linear,
Okay.
and you try to solve it by SLP.
All right.
So I think you guys are a little behind. You
Okay.
need to pay attention because when you are going to do regression and do SLP, you need some coding.
Mhm.
And also you are going to run 9 more nodal analysis.
Mhm. Okay.
So you need to speed up.
All right. Thanks.
Okay. Next.
name is Qiu Xiancheng, and he's my teammate Guanzhong. And today we got to present the the progress report. The topic is robot leg mechanism design optimization. And based on our previous proposal, there are many advantages of hydraulic mechanism, such as precise control and smoother motion. So we designed this hydraulic linkage with the goal of using an optimization algorithm to find its optimal parameter. And the mechanism has 8 design variables, and the objective function is to minimize theta 1 while maximize theta 2. We aim to achieve stable the body and maximize the range of motion in the same time. By applying the law of cosine, both joint angle can be computed, and the constraint is imposed via the triangle inequality, which means the sum of any two sides must exceed the third. It makes sure the triangle can assemble. And after obtaining the optimal parameter, we import them into Creo for simulation to verify the actual linkage motion and angular range, and to compare the result of two optimization approach. And next, we will introduce the process of optimization algorithm.
Okay, this time Professor mentioned that our flow chart has some logical inconsistency. And this is a revised version I created. First, we use GA to perform the initial search. As for the convergence criterion, we observe whether convergence has been achieved after reaching the maximum number of generations. If an optimal solution is obtained at the end, we then use that solution as the initial condition for the second search using the gradient method. For the starting criterion of the gradient method, we currently set it such that the process starts if the difference between two successive solutions is within 0.001, and if not, the search is restarted. And next, these are the results of our initial GA search. Along with the obtained all link lengths, and from the future, we can observe two major issues. And first, the best cost star close to 0 and remains nearly unchanged, which implies that the final solution may not actually be the optimal solution. And the second issue is that the mean cost does not seem to successfully converge toward the best cost. To address these two problems, our next step will be to modify the cost function and adjust the GA parameters. Moving on to our future work, we plan to integrate both optimization methods. Afterward, we will use mechanism simulation in validate the results. And finally, we will conduct a comparison. And here is our schedule. In addition to refine the GA, we will begin the second research using a gradient method. Once everything is complete, we will proceed with validation. And this concludes our progress report. Thank you.
Okay, can you go back to your convergence progress? Convergence, the next page. So, what does the blue curve mean? Best cost, what do we mean? How did you get the best cost? How did you guess the best cost? You can answer in Chinese.
我的 cost function 源是信达1指标，信达2，然后
So how do you know the best cost? Can you go back to show your design work? Design. Okay, so how many variables? 2? 几个变量？8个。几个变量？8个。OK， 8个变量。And 那你说什么 best cost？ 你怎么知道什么那些变量是多少才是 best？ 你怎么会知道？而且更满意。
它这边的 best call 是，它跑完，因为它是设200次迭代次数，然后跑完200次之后的最后那一次，就是200次里面会选最好那一次，然后
就是以例子嘛。那你那红色课要干嘛？就不需要红色的啊。你都已经以例程，你是第一轮就最佳了。你那不用算平均的 cost， 你是 GA 嘛？你的意思说有10个染色体，平均他们是多少？那不重要，是最好的。那表示你第一轮就最好了。那你第一轮就最好了，还有什么好最佳化的？你不用10个都很棒啊，有一个很棒就好了，就找到答案了，我管他其他9个要干嘛？对吧？所以你为什么会第一轮就找到最好？这是很诡异的事情。你有随机去 try 那8个变量吗？8个变量的东西，你可以随机 try 就 try 到最佳解，这太诡异了。
所以我这个结果会，我会要修改，因为它跑出来
一定要修改，一定有问题。
因为它跑出来我就知道它有问题，然后我更改它的。
你是不是那个每个变量的那个调整范围很小？就是说你比如说比如说第一个值叫430，你那个 range 是不是很小？300到。那就很诡异了，为什么你这 GA 那么强？第一轮从来没有第一轮就应该要这样子嘛？对不对？So please go back and check your code. So I think your problem should be complex enough, but something is strange in your GA. For each variable, how many digits did you use in the chromosome? How many bits? 16. So your GA can find out the best design with 16 times 8 long chromosomes in one iteration. It's impossible. Right? So something is happening. I don't know why. Okay, so please figure it out. But I like your problem. Yeah, so please just figure out what happened. And for the way you present the result, you don't need to show average of. Let me show. Are you showing the fitness? Cost is fitness, right? So yeah, we don't need to show average fitness. Show the best fitness. You should see this kind of trend. Okay, so please figure out. Are you relying on some kind of software? MATLAB GA?
We use MATLAB.
Is it possible you, in your every generation, GA has finished? What do you mean by
I know this is.
OK， 我说中文好了，是不是？你又不是每一轮 GA 都跑完，是不是这样？
因为我是
你回答我问题，拜托。 会不会是每一轮每一个 generation， 你的 GA 已经跑完，就是已经收录？我讲的是中文啊，就有一种可能，会不会是你跑了500次 GA， 然后你每次 GA 其实都收敛？我不知道是不是啊，那就才有可能这样嘛。
没有想到这个问题。
那就是因为你是学生，不是老师嘛。所以你回去看看，搞不好是这样，会不会你程式怎么写的，你根本呼叫了 GA 跑500次，然后你每一次呼叫，其实它里面都已经解老半天了，然后都给你最终解，所以当然每一次都找得到最佳解。我不知道是不是这样，你是不是写了一个什么主程式，然后呼叫 GA 500次？因为你那个指令 GA 什么什么，它就会解，它里面其实就会一直解到答案了。那搞不好你是呼叫500次，如果我猜中的话，请你告诉我猜中。OK， 因为我能想象的就是合理解释就是这样。那也是我要强调为什么不要依赖 software。你依赖 software 你就不知道发生什么事情，你就没办法，就是你要是写 project 或者你要做研究，你根本都没办法在这个 code 里面讲任何事情，你只能说你用 GA。你到时候很有可能你硕士研究你就是用 GA 啊，你这次没学会，你将来是会遇到，自己写是最好，相信我。OK， so please go figure out. OK, next.
Good morning, everyone. I'm Ping, and this is David. So, this is our outline. Multi-tray food dryer often dry unevenly due to poor airflow distribution. Even in recent design with multiple fans, this issue still exists. So, to improve airflow distribution, CFD has been widely used, and researchers have used methods like CFD, linear programming, GA, and ANOVA to optimize both design and drying parameters. So back to our topic, what is sequential linear programming? Sequential linear programming is an iterative optimization method. It is used to solve nonlinear problems by converting them into series of linear problems. In each step, the objective and constraint function are linearized. And to achieve better airflow distribution, we choose the number of fans and the distance between fans to optimize. So on the left side shows the reference data from previous study. And we finally select 3 slide fans for our optimization study. In the data, the airflow speed with 3 fans range from 0 to 3.3 meters per second, and the uniformity index was 71.6%. And the right side is our size of the dryer. So the main object of our study is to improve airflow uniformity in conversion type multi-tray cabin dryer. To do this, we use 2 main tools, CFD to simulate airflow pattern, and SLP to find the best fan position. And this is our workflow diagram. First, we have maintained statistical software to design experiment. Then we import the model into ANSYS Fluent to perform CFD simulation and analyze airflow distribution uniformity index. Then we create 3D model in SolidWorks. And after collecting the corresponding UI result for each DOE, we use ordering for ANOVA and curve fitting and develop the second order polynomial regression model. Then we use sequential linear programming and perform optimization on MATLAB based on the fitted model. Finally, we validate the optimized design point in ANSYS to compare the prediction airflow uniformity with actual simulation result. We employed an L25 orthogonal array experimental design, use SIM-Minitab to generate 25 design points. And the design variable will the position of the 6 pipeline, label P1, P2, and P3. Each fan position range between 207 and 355 millimeters. And we also set several fixed filters. And we use SolidWorks to build 3D model for the driver for each design point. And we import it into ANSYS. So a mesh dependency test was conducted to ensure simulation accuracy, to balance the accuracy and computation time. We choose a mesh size of 0.01 meter, which gives a high quality mesh of 0.999. And we use SST K omega model, which works well for prediction, shear, and turbulent flow, especially in high precision gradient and porous area like the wire tray. This model helps us simulate real tray drying condition more realistically. And we analyze how many iterations were needed for the simulation result to convert. And we found that airflow speed values stabilized within 115 iterations. So for our simulation, we set the maximum number of iterations to 150.
Okay, thank you. And then we go to surface plotting and curve fitting to obtain our regression model. We have used the origin software to create the surface plot. The data explains our uniformity index in terms of the 3 parameters, P1, P2, and P3. So we construct the surface plot and then go to sequential linear programming based optimization and validation. So we have implemented this optimization process in MATLAB. We guided by small step size around 0.01, so it can control our iteration and it will prevent overshooting, so we will not escape our optimal result. So the algorithm was iteratively updating until convergent, considering tolerance around 1 times 10 raised minus 6, and we consider around 1,000 iterations. So in each iteration, no linear objective function will be approximated to a linear model, and the gradient of the objective functions will be calculated. So this linear problem has solved using LP techniques. Basically, MATLAB's link prop function was utilized, which maximizes the linear function and approximates by minimizing our gradient function. So finally, after optimization, by using the percentage error matrix, we validate the verified result and compare the predicted and the actual safety results. So here is our results and discussion section. Based on our CFD results with 25 experiment design points, we plot our surface plot that explains our uniformity index value in percentage from 0.71 up to 0.76. In terms of P1, P2, and P3, it means the gap between the supply files. So it's around a 4-dimensional surface plot So we can see that it gave us an insight that how the factor levels influence our output variable non-linearly. So non-linear relationship obtained, and we try to create a polynomial regression model with an interaction of those three parameters to explain our uniform index function. So this is curve fitting result. Here the dots are explaining our data points obtained, the actual points. So after curve fitting, this kind of model has obtained, explained, and with this function. So after having our regression model, polynomial regression model, we was trying to see how the data of the predicted and actual values will lie together, or what kind of fitting would have. So the red line is showing the ideal fitting, means where the predicted and actual values would have, are gonna be equal, or perfect prediction would lie, but the points closer in the ideal fit in blue points are indicating good model accuracy and consistency, which is supported by around 92.47 R-squared volume. So keeping that, we go to sequential linear programming based optimization. So our objective is going to be maximizing our function, so we can maximize the uniformity. Under constraints, that means the gap between supply funds can be minimum 207 for each positions, and it can be maximum 395. So we apply CFB in the model. The optimal position of supply funds and the multi-drawing combinator are successfully identified or obtained. P1 around this much, P2 around this much. That means that's closer to the higher bound. And P3 the same, that P1 is around 357, which achieves a maximum uniformity index that's around 0.766, I mean 76.6%. So these results demonstrates for us both stability and effectiveness of our SLP model, navigating and optimizing in a nonlinear design space. So the convergence plot in this figure explains how steadily the uniformity index is increasing with rapid improvement up to 200 iterations, maybe up to maximum 400, followed by gradual stabilization as the algorithm approaches to the optimum volume. So here is the surface plot and the control plot by fixing one of our three parameters. So here is we can see linear graph, I mean smooth graph, because we already fixed the third parameter, and this is P1 and P2 versus uniformity index. So after that, after having the optimum values, we go to validation. So we can see the percentage here, it's around 0.48%. So already the objective function is nonlinear, and it's derived from multiple approximations. The SLP method gave us an approximated optimal result that proves reliability of our optimization process. And very small error was obtained, so it indicates the efficiency of the SLP method. And a small step size for sure controls our search direction and reduces overshooting and instability. So this result demonstrates both stability and effectiveness of our SLP. So when we see the final result, after sequential linear programming, we have got around 0.7697 uniformity index. That is the validated one with CFD after applying the optimal geometrical values in CFD. It's a little bit greater than what we have got in SLP. So it's approximately means 77%. But initially, before optimization, we had a uniformity around 71.6% or 0.716 in terms of index. So in this condition, our airflow speed range was between 0 up to 3.3 meters per second, as we have been explaining in our previous presentation. So then now we can see that I was trying to minimize the bounds so we can understand well. It's mostly between 0.6 up to maximum around 2.05. So we can see the colors of the streamline. So the flow speed range becomes a little bit smaller, with the average area-weighted airflow speed around 0.8 meters per second on the entire drying area. So initially we was explaining that one of the constraints is we need to have around 0.789 meters per second on our entire drying unit as average airflow speed. So since we are getting 0.8 meters per second on the entire drying unit as average airflow speed, so it's also a success. So So when we're gonna see the contour, we was trying to make very clear and imaginative way with different colors. This is the maximum airflow speed that's gonna be supplied by the fan. So still there in the supply fan domes, there is still high velocity, but most probably in the trees we can see that quite probably uniform distribution there. Without including the exhaust fan, but now this uniformity can be explained numerically around 77%, but it still needs improvement. So here are the references we have used. Thank you. We have finished our presentation.
Okay, great. One question about your SLP. It seems like, think about it. You have a design space with variable bounds. So basically, variable bounds in all three P1, P2, and P3, right? And your object function obviously is nonlinear. And if you linearize it as a plan, so obviously your solution will bump into one corner. And you're doing this sequentially, so in this new position, you will have a new approximation of the object function, so you will have a different slope. So that will lead you to a different position. So basically your design point will be moving around in the space, sequential with this change of slope of your linear approximation. So I guess when you apply this MATLAB code, it seems like it only allows the design point to move a little bit, not all the way. So is there some kind of step size setting in this sequential linear programming? Okay. So right now you have such a small stepping size. So you require 1,000 iterations to converge. Is there a better way of controlling it? Maybe you can move faster in the beginning and then slow down.
We have tried the one first.
But it doesn't work well?
Doesn't work well. The uniformity is very low. And I think it was that it keeps the optimal. So we try to manage it.
Can you, Michael? I hear you.
Okay, so first we use the step size, not 0.01, 1.
Right.
And then 0.1. But when we are...
So you manually control it?
Yeah, we were trying to control and see, I tried to check what's the maximum volume.
Yeah.
But the most possible maximum value was a 10 when we make our step size smaller. And when we were trying to explore why it happens, when you are making your step size smaller means you are trying to find your optimum value within a very small way.
But it's not good for optimization.
Yeah, it's not good.
It's costly.
Yeah, it's costly. But in our case, we are looking for our optimum point. We are not thinking about our cost.
There are certain issues in the problem you are solving.
Yeah.
One thing, I think your response is quite nonlinear. So can you go back to one of your response surface? When you try to, from here, you can already see the real function itself probably is having an order higher than 2. So now you are using projecting, second order.
Second order, yeah.
So your approximation may not be able to fit to the real model the best. That's one issue. Okay. Let's say we use second order. You may still fall into the local minimum. So I think one thing is your function is very nonlinear. You may have multiple local minima. So SLP is still relying on gradient. So you may want to try multiple starting points and compare their results. But I would say try not to move so slowly with such a small step size. You can try multiple starting points to avoid local minimum issue, but just speed up the iteration process. And there's one strategy, so-called I think people call it trust region. So like at the beginning, I trust the entire region. So I have a very large step size. And then every time I iterate, my trust region shrink a little bit. So initially in the space, maybe I'm here. I am actually exploring the entire space. So my first move is gonna be super large. So when I move on to in the second iteration, okay, maybe the solution is somewhere here. Now I shrink the searching range a little bit, maybe multiplying 90%, 0.9, but use that new position as a center. So I shrink a little bit. And so you will be moving slightly shorter than the earlier one. And then you shrink again. So you will be zooming in gradually.
So it's just like revising your design space.
Yes, it's like shrinking your design space gradually with your iteration. There's a kind of strategy like that. Yeah. So that avoids this kind of a slow movement. So try those. So maybe you can have multiple starting points and then this shrinking design space strategy. Okay. And let me see what else. Oh, by the way, for the representation of your response, I would recommend you to use, because it's a 3D problem. So the function value is the 4th dimension. I recommend you to use iso surface, which means multiple surfaces, but they are like impermanent. So you know, in fluidics, people use that all the time. So it's like something like this, like a surface here and then another one here. So you have, this is your x1, x2, and x3, but this would be function value 1, function value 2, function value 3. It's like a pressure field, iso surface. So how do you plot something like this? You basically plot out your whatever function you have, but at value of f1, and then plot another one at f2.
So you can have a ladder.
Then you will have several isoplanes. That's a better way to represent.
So can you surface fit within this?
No, it's the same function, but it's the way you present it.
And just to show.
Just the way you show it. So if you allow this equals to a certain function value, then originally you have 4D, right? But once you assign a function value, so that one is set, becomes a 3D. So then 3D surface can be plotted.
So it means it's just having a lot of 3D surface parts together in one.
I'll show you one paper and then some code later on. So then you can better understand. If I forget to give you, remind me by email. Okay? Yeah. So I think, and also for your story, for the entire presentation, the storyline is too long. I think at the beginning you guys mentioned CFD, GA, ANOVA, but similar information has been mentioned multiple times. So you can kind of shrink your presentation and then just get to the point. Okay, CFD. Okay, just mention CFD once. Okay, I'm gonna use DOE. Okay, just step by step, because you already have a lot of steps, so you don't need to make the story too complex. Okay, thank you. Okay, next.
Hello everyone, I am Tejal and I will present my progress report
In this project, I aim to improve trajectory tracking performance in drones by tuning LQG controller parameters using genetic algorithm. So, to give a brief overview, LQG controller is a more advanced controller. It is a combination of LQR for optimal control and Kalman filter for state estimation in noisy environments. The problem is LQG controller is highly sensitive to parameters such as QR for the LQR part and WV for the Kalman part. Moreover, in the 3D drone control, each axis, roll, pitch, yaw needs independent tuning that makes a total of 21 parameters to optimize, and systematic method like genetic algorithms becomes necessary. So the aim and objectives of my project are to optimize the LQG controller for robust 3D drone trajectory tracking across diverse paths using a genetic algorithm, ensuring generalization beyond a single trajectory. So my objectives are to model a full drone dynamics with the position, orientation, velocity and angular velocity, implement a 6D LQG controller for position and velocity control, design a genetic algorithm to evolve 21 LQG parameters, and include different shape of trajectory in optimization, and test controller performance across multiple paths to ensure robustness. So now let me explain why the 21 parameters of the LQG. This is the core of our optimization. In this project, we are building a 3D LQG controller to track a drone's position and velocity in X, Y and Z direction, not just its rotation. We define a 6D state that includes drone's position and velocity, so where it is and how fast it is moving in all three directions. The LQR part of the LQG uses two matrices, Q, which cares about how far the drone is from its target position, if it is moving fast, and R, which keeps the control effort like acceleration. So we check like we don't overdo it. Then the Kalman filter helps the drone figure out its true positions and speed despite noisy sensors like IMU. Here W captures the uncertainty of the drone motion such as wind, and V handles sensor noise. So in this table I have described all the number of parameters for each component, and it totals to 21 parameters. So this flowchart outlines the core steps of my project. I started by setting up the simulation and implementing a basic 3D LQG controller. Then I test it under ideal conditions to establish a baseline. Then I will introduce a noise to simulate real world challenges. And I'll design a genetic algorithm where each individual will represent 21 LQG parameters. So for my experiment, I started for implementing the LQG. I started by initializing the simulation environment. So first I set up the drone control. I defined the drone state and the set of simulation parameters like the starting of the simulation and the total time we want for the simulation. Then the LQG controller is initialized with manually set matrices like QR for control gain tuning and WV for Kalman filter noise modeling. And we pre-compute the LQR gain K and Kalman gain L. Then then we give the input as the reference trajectory like circular, rectangular or slanted circular. For each time step we extract the reference position. Then we simulate the drone motion. The control input is applied to the drone model we simulate realistic drone behavior using full nonlinear dynamics integrated with RK4 method, which is Rankutta method. Then we get the sensor data from the drone state. We extract the observable 6D state and we simulate the measurement of noise based on matrix V to mimic the real world sensors. And the Kalman filter uses noisy measurement and the process model to estimate the true state of the drone, and this provides a refined estimated of position and velocity. Then we, based on using the estimated state, we and the desired reference trajectory, we compute the control input, and we also apply altitude boost and orientation correction to stabilize the drone. Then if the simulation hasn't reached the total time, we loop back up to apply the next reference point. If the time is complete, we proceed to evaluate the performance. And after completing the simulation, we extract the actual trajectory, tracking error and control input logs. Then we check the performance, like if the errors are too high, it indicates that the current LQG parameters, that is Q, R, W, V, are not sufficient, and we retune the parameters and restart the control loop to improve performance. And if the performance is acceptable, we stop the trial and try the genetic algorithm for different trajectories. So I want to show the yes.
Left. Now.
So I tested the basic LQG controller on a circular path for 20 seconds and it did pretty well. Tracking error was under 2 meters. And then when I kept the same LQG parameters and tested it on a different path, it doesn't perform well. So it's like it is overfitting on a particular trajectory. So further I aim to the error can be seen like it shot up to over 5 meters, especially at the corners. This shows that the controller was too tuned for the circular path and struggled with the other parts. That's why we need a genetic algorithm. So it will optimize the controller to handle all these parts better. So in conclusion, I have implemented a realistic quadrotor simulation capturing position, orientation, velocity and angular dynamics, and developed a baseline LQG controller for position and velocity control, and tested it on circular trajectory and verified controller on new trajectories. Performance degraded and matrix tuning was needed. So next I will integrate a genetic algorithm which will be used to optimize the 21 LQG parameters across diverse trajectories like circular, rectangular, slanted circle. And the genetic algorithm minimizes a combined fitness of average tracking error and weighted control effort, which will achieve a generalized but and robust LQG controller that adapts to varying paths and disturbances.
Okay, I have one question. Can you go back to your integral formulation? Yeah, so basically your LQR cost is an integral of all costs along the entire path. Am I right? So in your animation, it seems like you have a desired trajectory and you have a starting point that is far away from the desired trajectory. So, does your overall cost also include your starting state and also the difference between your starting state and the trajectory?
No,
No, it doesn't include.
No, I have just set the starting point, so for any path it will start from the same.
So basically, there's the circle you design is right here, the UAV is right here. So when you say start, based on common filter, you will have a large error initially. So the common filter will try to move, but do you already assign which is the starting point of the circle?
No.
Okay. So think about common filter. Common filter basically compares a desired position and a current position. So you may need to figure out what your common filter is doing. Is it trying to stick with one starting point in the circle, or it's actually the closest? It seems like there's a specific point. So common filter is supposed to move your vehicle and then move as close to the target point as possible. And as time goes by, your desired point moves as well. So timing is also a weird thing in your program, because this is your time zero, and this is your desired circle. Let's say there's actually a starting point, starting desired point on your circle, and maybe that's time zero. So when this is about to fly, and maybe for the computer, the desired point moves as well. So maybe when your UAV is already close to the circle, your desired target point is already in front, like move along the circle. So you are trying to chase. So maybe that's why your trajectory is not very circular at the beginning. And once it gets onto the point, then it follows. So see if you observe a speed up planning at the beginning and then slow down at the end.
Yeah.
Then that's fine.
Oh.
So you in your code, let's say on the circle there are 100 waypoints. As time starts from time zero, your code gradually move your desired point from the first waypoint to the second and keep on moving. But you are far away. So your desired point initially is here. As it's close, your desired point is already up to the other position. That's why you need to speed up. Once it chases up to the point, then you follow. So I think when you draw the desired trajectory, in this particular problem, you may also need to draw a desired line. Or maybe your airplane is already close to the circle. Or in your common filter, because think about indoor positioning. First you need to know where your robot is, and then you need to know where is your target, and then in the computer draw a trajectory, and then allow the vehicle to move. So usually the vehicle is on the trajectory already. So the goal of common filter is to follow. As it moves, see if there's error. If there's error, minimize it. So the vehicle will be moving like this, and then eventually get to the goal. But now your initial error is so large. So something chaotic may happen. So maybe in your second example is basically due to that strange issue. initially you have a start error. So maybe in your second example, and if you put your vehicle right on the beginning of the rectangular point, then you will do well. So go figure out, okay? And let's see. What if you, when you resolve this issue, you put your vehicle onto the right starting point of the circle? What if your SQL, LQG controller is already doing well, following well? Then you don't need to do GA. Right? Yeah, it's possible because you're using common filter. Common filter itself is an optimization. Yeah, so can you go back to your formulation? Yeah, here. So LQR is a way of formulating the agility function. Basically, the way you define your error or cost. And common filter is a way to minimize error along the way. So actually, this itself is an optimization. But I think you are using additional optimization. You try to use additional optimization to tune some of the user-defined parameters. That's what you are trying to do. But usually, you will do it when this is not doing well. So probably first, get the simulation right and see if this is already doing a pretty good job. If so, then enhance the complexity of the trajectory. Maybe doing a very three-dimensional trajectory, then definitely your controller won't be able to behave as well. So you will see some weakness of the controller and the common filter. That will be the time you apply some optimization to tune the parameters. Yeah. So yeah, I like the research, but please make sure you are doing something like that. Okay. Thank you. Okay, next.
Good morning, everyone. And my name is Chong Wei Hao, and my teammate is Deng Youjia. And today we will present our progress report about the optimization of reconfigurable finger mechanism based on deep reinforcement learning. And this is our outlines. And first, we will talk about a quick overview for our project. And in this project, we want to use the reinforcement learning to optimize the motion of the reconfigurable fingers mechanism. And our main goal is to maximize the range of motion of the fingers and effectors, and in both modes. And in this project, we face some difficult challenges. And because the reinforcement learning requires interaction with a simulated environment, so we need to build a customer real-time kinematic simulation. But this mechanism is very difficult, and it will change the multiple modes, and it have multiple kinematic loops. And we try to use some software and find some software, maybe have some API we can just input it, but we did not find the software. So we can just get the trajectory data from the software. And next we will talk about how we implement the kinematic function.
At this stage, we use the vector loop method to determine each link length, taking the ground link as the coordinate reference. We formulate 3 vector loops, the first for the first flanks, the second for the second flanks, and the third for the slider. By projecting each vector loop onto the x and y axis, we obtain 2 scalar component equations for every loop. When the mechanism switches to the rotation axis constraint mode, only 1 degree of freedom remains. Hence, the first and second flanks can be treated as a single rigid link, and the 2 sliders can likewise be combined into another link. This reduction yields 2 vector loops. After simplification, we obtain equation 2. When the mechanism switches to the translation axis constraint mode, the flanks are considered together with the slider. So the first and second flanks and the slider are each treated as single rigid links. This gives 2 vector loops. After simplification, we obtain equation 2, which is then converted into x and y component equations, and solved as a simultaneous system.
And so far we have developed a kinematic model in Python by ourselves, and we can visualize the robot fingers models, but there has some incorrect as shown the figure, and you can see the theta equals to 30 degrees and theta equals to 60 degrees. The prismatic joints have some problems. Yeah. And this is our usual voice. We need to debug and validate the kinematic models, and maybe discuss with professors Yanhua Lin. And second, we need to speed up the development of the reinforcement learning, and we need to design and test the reward function. Yeah, and this is our presentation.
So Professor Yanhua Lin and I went to mountain climbing yesterday. We were talking about this problem. So the issue probably happens at the singularity point.
Yeah.
So are you solving kinematics by solving the equations, like analytically?
We use
or numerically?
Yeah, numerically.
Numerical solver.
Yeah.
Yeah. He mentioned for singularity configuration, probably needs a numerical approach.
We have tested the theta equals 90, and we found that the theta equals 90, it has a singularity problem.
I mean, his research is focusing on singularity.
Yeah.
So that's why the kinematics is not easy.
Yeah.
Maybe we need to have a small meeting with him.
Yeah.
Because if you don't resolve this issue, there's nothing to present in the final presentation. Okay. Okay, we need to have a conference meeting after this. Because it's not an issue about optimization, it's an issue about mechanism. Okay. Okay, but let's have meetings this week.
Okay.
Otherwise, you guys have no time.
Okay.
Okay, next.
OK， 好，this is our progress report. Thanks. This is our abstract. Our goal is to build a reality system for the mobile robots, and we use TPE allotment. This traditional TPE has a limit because the parameter lambda and gamma is under dynamic environment limit adaptive learning. So we propose a slope-aware TPE method. Let's consider not only the prediction of score FP, but also the sensitivity of the FP. And initial results show that stable parameter converge and contest work. So let's show it. It's a simple introduction of ST-ReID. ST-ReID has two parts of the identifier. The first part is visual feature. The second part is spatial temporal context. It says that where the person appears and when they appear. So the formula of the visual feature and the spatial time modeling is like this. We have two black boxes. The first black box is visual feature. The second black box is spatial modeling. So we can't modify the black box, right? So we modify the P joints. We just modify the score calculates. So if we need to modify this, we need to understand how the parameter work with the scores. So the parameter gamma will higher the scores. The lambda will lower the scores. They are by the function in the left-hand side, right-hand side. So we can say that the left part shows that as gamma increase, small change in x leads to larger output. The right part is that as lambda increase, the curve shifts to the right and require higher x to achieve the high scores. So here is our method of TPE. TPE is based on static, right? So it has a static calculate force. So first is initialize the lambda and gamma and evaluate the lambda gamma to compute the score FP and FP plus F prime P. So we will select top 25 good data sets to fit our pairs. Then the pair is to fit KDE parameters. So we will generate the new lambda and gamma, and we will make it a loop. So it will converge to a lambda and gamma we want. So here is the problem. When we first try to converge it, it's converged too fast. So why it's appear? The lambda one is collapsed to the lower boundary. The gamma one is tend to structure the upper bound. It feels like it's too sensitive. So we can modify the TPE target function. Okay, this is our modify. So we want the score to consider the high prediction confidence and high slope sensitive. So we dot f prime p, then f prime p is like the function below, and we can show that it's significant. The slope is class on this. We can take a look. We get the fit from this to this. Yes. So we figure out how to optimize this. So we need to establish the mobile robot vision. So the mobile robots will set it as a circle to see people work by camera 1 to camera 2, right? So we can just appear 1 as angle theta, and we set the theta is 60 degree, and appear 2 as angle theta 2 in 120 degrees. We can estimate the transition time, so we can use Insta like. Oh, I'm sorry. So we can use Insta like this. The Insta has 6 cam on the on vision, so we can use Insta to simulate multiple camera on mobile robots. And yes, the mobile robot will use TPE to adjust the environment, so to generate the gamma and lambda. So here is the robot system. The camera will capture the frame, and the YOLO will crop the person. The reality will capture the F vision and FST to F score. F score will set the fusion score to TPE, and TPE will update the lambda and gamma like this loop. And so here is our, yes, it is our demo space. The camera will see me and generate an ID. Then the ID will convert to 1, like this. CDO C6 FA, yes, I is. So the method is called decision layer of the construct real ID database update. Once the ID is generated, it will push to the dynamic feature DB, and the dynamic feature DB will assign the simulated batch to know who I am. If it don't know who I am, then just retrieve a new ID. So here is our conclusion and our TP demonstrates. So our conclusion was student-aware objective FP and F1P is efficiently prevent the collapse of lambda 1 and maintain adaptive behavior in the future. The received TPE alignment is stable converging spatial periodic space lambda 1 and gamma 1. The visual base parameter lambda 0 and gamma 0, it can be fixed in a robotic setting. It's just focused on TP adaptation on temporary constants. The preliminary results the featureability of the intelligent ReID, YOLO, and dynamic ReID is into the mobile robots. Yes, this is our reference and second.
Okay, can you show me the F again?
Yes. This.
Go back. Keep going. I need to know what's your F.
Okay. This is our target function.
So what's the meaning of it?
Oh, it means 2 strings of vision and spatial time modeling. It will calculate 2 scores to calculate the P joint scores. So it's just like this.
I'm talking about your. Let me think about it. So what is lambda? What is gamma?
Okay, the lambda or gamma is like adjust the modeling to
like a shape function.
Yes.
Okay. So so basically you are building some kind of exponential function. So why this shape? Maybe the score is not having this kind of shape with respect to your x.
Oh,
how do you know it's like this particular shape?
Oh, that's a good question.
Of course.
We can see like this. Okay.
No, this is f times f.
Yes, and I can.
F prime, f times. So are you minimizing or minimizing?
Okay.
Are you minimizing or maximizing?
Can I use?
I'm asking you, are you minimizing or maximizing? You're maximizing.
Maximize.
So you maximize the score times its slope. That means you're looking for a position that is having the highest score, but also the increment of the slope needs to be large. Yes. But in optimization, sometimes you are looking for zero slope.
It's not quite. Okay, I think I need to explain in Chinese.
OK， 那我也用中文讲。你最佳化的时候，有时候你要一个，不管你要最小或最大化目标函数，有的时候在那个地方斜率是零。
是。我们在假设的一种情况是说，因为这个公司啊，它的视觉特征它没有办法被 simulate 出来，所以我们是用时空 simulate。我先假设了一个人从
你都没有讲重点，重点是说为什么一定要？你现在就是有一个东西叫分数嘛，这个东西叫做你的 whatever x， 对不对？
是。
那问题是，你为什么要用这个数学公式？你怎么知道这个 behavior 是这个形状？
是
对。那我只想要知道为什么是这个形状。That's it. That's it. 然后这是一个 first question. Second question. 为什么你要 maximize f 乘以 f prime？OK， focus on 这些 question， 拜托 ，please。
我们在 maximize 它的 score 的时候，是想要知道这一个人最大几率会出现的位置，就是他是从1号摄影机走到。
先讲function type。
对不起。
上面为什么 f 长那样？
是，它是一个曲线函数，它出来是一个像中型曲线的东西。那它可以透过浪达跟伽马去调整这个中型曲线要左移或者是右移。那它的
很多数学形式都长这样，为什么选它？
是因为它是一个比较常见的平滑形式，在统计学上的话，
那你有做过一些 sampling， 你就知道说，因这个 behavior 跟你期望的是像的。
目前来说，它的数据都和论文的数据是相符的。是。主要是论文还是他选择这个方法。
那就是说，这是一个非常 nonlinear 的 function， 你就要 maximize 它，对不对？
对。
那为什么要乘以 f prime 呢？就是不 make sense。
是我们要乘以 f prime 的原因其实很简单，就是因为我们在 TP 的时候，
你在前一步的时候，是。你现在只是说迭代的时候。这找的那个效果跟你想象的不一样。
是。
那因为你的函数是非常的 exponential 的这种东西，它就会急增或是急降。你的问题是这样。
是的。
有时候就是 take a logarithm 就解决。因为你找到那个答案不一定是 maximize f。
是。
因为你的目标是 maximize f， 那你的答案不一定是 maximize f。那它不一定是答案。虽然说你最后结果看起来很好，但是你同时也 maximize f prime。你如果 f prime 还很大的话，就表示可能不是最佳解。你懂意思吗？
对。我的主要想法是 f prime 它会表达这个还是它的 sensitivity。所以
是 f 是 score 跟变量之间的关系。如果它还不是0的话，就不一定是最佳解。
好的。
对啊，所以你要去想这件事情，就是说这个 这个 object function you're trying to optimize the function， 对不对？那这个斜率应该要越来越小，你却让它越来越大。
它那个是正常现象，就是因为mean time 的增加会导致让达跟伽马会逐渐向一个方向去收缩，所以它
相信我，
好的。
讲这件事情，就是说，以数学的角度来讲，你没有在做你该做的事。数学的角度是你要 maximize score， 你就应该 maximize score。你如果做了一个 extra 的事情，但是那跟你原本 maximize score 可能会违背，那件事不一定是好事，你可能在做别的事情。那除非你要做的事是另外的一件事，那你就要解释 maximize f 乘以 f prime 代表什么。那结果长得怎么样，搞不好都很漂亮，但是呢，它的意义上是不一样。你要做科学的话，你就是要你有一个 goal， 然后你有个数学的定义，然后达到效果，就是你提出来的 idea 跟你提出来的 information 要 match， 你的解释不 match 的话，那你就没有在做你想做的事。你 obviously 你就是要 maximize score。那我不觉得 maximize at prompt 对，那除非你在做别的事。对，
我会在修这一大题。
Please think about it. Okay.
As I already mentioned, we are using the gradient and the genetic algorithm, and later on we will compare both the results. And we have done the gradient descent method. These are our objective function. We are minimizing the weight and taking stress and the displacement as a constraint, and the perceiving and yield also. And our design variable is the area only, and the total cost function we calculate as the weight and the penalties. We already decided the penalties like yield penalty, buckling penalty, displacement, and minimum area. If it will exceed this value, then it will charge as a penalty, and then you will return back to the original. And this is our design. We are using 10 bar truss, and we define the nodes of the. And after that, we define the material and the load, and allowable stress is 122.25 megapascal, and the allowable displacement is 50.8 millimeters. And now we start with the finite element analysis. First, what we have done, first we define the stiffness matrix of individual element. An element has two nodes. Like when two nodes connect, one element will make. So like, and one node has a two displacement, in x direction and the y direction. So we calculate the stiffness matrix of the individual. After that, we will compute this individual stiffness matrix in a global stiffness matrix, which will define the whole truss. After that, we apply the boundary condition. As I already mentioned, we fix our node 5 and 56. So there will be no degree of freedom, and other will be some displacement. After that, we will solve our nodal displacement. UF, KFF, we will already, as I already mentioned, we will define the global stiffness matrix. From that, we will get the KFF. And the FFF also we will decide. After that, we will compute member axial forces and stress. in the individual element, we will define how much forces it's experiencing. And after that, we get the forces, we will simply calculate the stress of the each individual element. And now after that, we will check if that the stress and is lying in our criteria, like it's not over-converged or disconverged. Then also we will also check the buckling and deflection. And now after that, we have done the gradient descent method and gradient descent optimization. We start with some initial parameter. We guess the area A0. After that, we compute the FEA and the cost. And for the current A0, what we have selected as the initial guess, we calculate FEA. And if he has some penalties, like if existing the stress, then we will charge some penalty. And after that, we compute the total cost, which is weight plus penalty. After that, we have done the finite difference gradient. Like we find the gradient, and like for I1 to 10, we have 10 members, and we are giving wiggle to one truss and one element, and the rest of the element will the same. And we will see how the cost function will deflect, what the cost function at when we will give a wiggling to the one and the rest of the same. And after that, same like we will do the wiggling to the another member, and the rest of the will be same. After that, we will get our gradient. And now we will update our areas formula, like A minus alpha, which is the step size, and learning that we can say, into gradient descent. And to not exceed to the area, we clamp it, like it should be the minimum 65 mm square and maximum 2932 millimeters square. We clamp our area. After that, we will check the convergence, and we are doing this for the 300 iteration. If iteration 300 iteration is completed, then it's converged. If before that, it's 10 to the power minus 4, then it's converged. After that, we will get our area, optimal area, and displacement and the stress, and at the end we will plot our graph. And if not converged, then it will again move for the second iteration. And this is the result we got. And we define the node, and length is calculated by the MATLAB. And we got the area of each member. It's the optimized area. And this is the optimized, like the stress in individual element. And after that, we got our mass, what we are doing, what we were objective function, and like each individual mass. And after that, at the last, we have calculated the total weight, total mass of the truss will be 6.95 kg. And after that, we calculated the weight. Weight is like the gravitational force into the mass, and we find our maximum weight 68.2 newtons. And this is our nodal displacement. As I already mentioned, each node has a two displacement, like in the x-axis and the y-axis. And we are using the 6th node, so we have 12 node displacement. As I already mentioned, we fix node 5 and node 6, so there will be no displacement. So that's why I have mentioned 0, 0, 0 in the last. And this is our optimized truss what we got. And this is the dashed line will show the undeformed truss. Colored lines show the optimized design under load. And the member are color coded, like the blue is showing it is experiencing as a compression, and the orange and the red line will show it is experiencing the more tensile load. And the green and the yellow shows stress shows it has low stress, we are using this. We are plotting this stress using the final area what we get after optimization. After we will, what we can check, like there is a maximum deflection is 0.01, which is lying in our criteria, and it is following the constraint, and all our stresses are below to 172 megapascal. That means the serviceability and safety limit. So, like I already mentioned, the cost convergence, the main motive was to minimize the cost. In the iteration first, cost reflects the initial midpoint, there is no constraint violation. So it's a pure weight. After that, it has some violations like stress and other violation buckling. So it got the penalties and again rise the whole cost. After that, we clamp the fourth the invisible area back within the minimum and maximum, between the minimum and the maximum. And the software penalty exponent is still dominant, but cost return near the original weight only level. And the flat line afterwards till 300 iteration, with area of the stack as they are bound and penalties unchanged, gradient to vanish. And the cost remain constant, no further downhill direction to the reduced weight plus penalty in the current setting. And the future work we are going to do the implement genetic algorithm. After that, we will compare the gradient descent and GA, and especially the weight and the computational speed and the robustness. And if we got enough time, then we will apply the multi-load case node layout. Like for now, we are applying load on the 2 nodes only. Thank you.
Okay, one question. In your optimization, are you considering the constraint?
Yeah.
But you are using a gradient descent. Then how do you handle the constraint? Gradient descent is an unconstrained optimization.
Like I already mentioned,
you never mentioned. Okay. What do you mean you already mentioned?
Like if we are taking the constant, if our when we run the FEA, if it is exceeding the stress or
okay. So what are the constraints? Show me the constraints.
Like the buckling.
Show me.
Yeah.
So they are
like the buckling.
They are inequality constraints.
Yeah.
They are not finite element equality constraints. So in optimization, if you have all these inequality constraints, that means you have a design space bounded by your constraint functions. So the solutions are in here. If you have a gradient-based approach, the gradient may lead you to somewhere outside. Your strategy have no control of pushing these points back to the physical space. So how come your gradient descent method can find a solution inside the space? That's what I mean. If you formulate Lagrangian, then it works. But I don't think you are working on Lagrangian. So it's very strange that you have a solution. And also your iteration process is very weird. Going up and then come. Did you start with a solution? Did you start with some solution you already know? So it seems like right there that initially you have a pretty good starting point. And your method leads you to something somewhere bad and comes back to the same point. So did you start from a good point?
Like we just initial guess.
So you are like a god, you know where the solution is. You start from the optimum. You have to start from some random starting point and see if the method works. And I can tell you, it won't work because a gradient-based approach cannot handle constraints, right? And go back to your flowchart. What do you mean by flowchart? What do you mean by penalties?
Penalties, if the stress is exceeding 172 megapascal, then we charge like we will add.
So this is Lagrangian. This is just like Lagrangian. You put your constraint into the objective function, but you don't have a Lagrangian multiplier. You basically penalize the constraints.
Yes.
That's how you did it. So you should be answering me with this equation. You need to be answering, oh, I handle the constraints in this formulation. I use a penalized formulation. But how do you control the penalty parameters?
Like we initial get some yield, some buckling.
So that's not a good way. You should follow Lagrangian. Because Lagrangian has a Lagrangian multiplier. Lagrangian multiplier is considered as one of the variables. Optimization handles the decision of the Lagrangian multiplier. So in your formulation, you make a decision of the penalty by yourself, but you are not God. So if you choose a penalty parameter inappropriate, you may fall into a bad solution. Okay. So see if you can handle this with Lagrangian formulation, with Lagrangian multiplier. Yeah. And because all of these are inequalities, in this formulation you need to convert everything into equalities. You need slack variables. So you will be having a lot of variables. But that's okay. That's one way to do it. Okay, move down. Keep going. I don't like the clamping strategy. So maybe the clamping is for variable bounds, right? So if the solution is outside the bound, okay, stay on the bound. Treat the bound as constraints and put it in the Lagrangian. Because if your gradient-based approach bring the solution to somewhere outside of the bound, put it back, next time it will move out of the bound again, it will be an infinite loop. It doesn't stop. It doesn't guarantee the clamping will stop the iteration. So clamping is never a good strategy. So if you have a clamping strategy, then you may need a iteration, maximum iteration number constraint. But it's not a good way. Okay, so usually just put the variable bounds in the objective function as well. Then you can move forward. Okay. The K for kg is kilo.
Yes,
Kilo is a small case K. Kilo, small case. Yeah. So it's important because mega is capitalized N. That's correct. But kilo is a small case K. So pay attention to those. Those are important. Okay, move forward. Keep going. So what are the color representing? Stress?
Yeah, it's stress. Like which element experiencing which kind of stress.
Okay. So in your case, you have red color.
Yeah.
But in your color bar, where's the red?
Yeah,
No, you don't need to change anything. Just look at your color bar.
Yes.
There's no red.
Maybe it's exceeding the bar, rigid bar.
Maybe you are not being careful enough. Okay, so pay attention to those. Otherwise, this is not making sense. Okay. And also, on your left lower corner, you mentioned 172 megapascal, right? But in your figure, in your color bar, you're representing numbers multiplying 10 to the power of 7. Maybe that's Pascal or whatever unit. How do people match with your numerical expression and your figure? There's no unit on your right-hand side figure. And they are not presenting in the same scale. So those are important. This is very weird. This is meaning your optimization process is not doing the doing its job. So usually it's something, oh, okay, stop, right? It never goes up and then, okay, go back, and then elongate for 8 more iterations and then stop. It's very weird. If you're doing things right, it will stop at the 4th iteration. How come it doesn't stop at 4? How come it stops in 11? Maybe your computer code say, okay, run 10 times, run 11 times, and then stop.
We run for the 300 iteration, but it is stop at 11.
So you're definitely doing it wrong. Your termination criteria is not functioning. Your termination criteria is not terminating your iteration. So there are many weird settings in your problem. So I would say focus on this. Do not move on to GA or whatever method. Just get this right. Okay. This is already quite complex. Okay. And once you are making all the optimization right, get a final design, run the instance on that particular design again to verify whether it's a good one or not. Okay, thank you. Okay, so that's it for today. I'm sorry on the overtime. On the final week, we need to do a better job on time control. So that's it for today. Next week, next Monday, is the 26th. I have an important meeting in National Science and Technology Council, 国科会, so I cannot be here. So I think because we are on schedule, I have taught many things I want to teach for the course. So I will. Is it okay if we skip one course? Yeah. So next week we will skip it. 2 weeks from now, which is June 2nd, that's the final week. So the next time we meet is your final presentation. Okay? So you guys have 2 more weeks to work on the project. I gave you several comments. If you are not clear about anything, you may need to send me personal message. I will give you the ISO surface reference. I can talk with you about the formulation, and I can check your code. And so every group may have some issues. You can send some message to me, and we can set up certain personal meetings, so we can work on this particular problem before your final presentation. So on your final presentation, focus on the presentation. And I know you need some time to write a report. On 2nd of June, presentation file first. So if your final report is not done, I can give you 1 more week to write a report. So focus on whatever you are doing, coding and whatever, and then your final performance. And maybe your report is only 60% done. I give you 1 more week to finalize. Okay, so June 2nd, presentation. June 9th, submit your document. Okay, and I saw many of your work are doing pretty good. I would like to recommend some of you to some conferences for this year. So it will be fully paid by my lab resource. So for future recommendation, I will personally contact the group. You can refuse me, that's fine. And you can say yes. If you accept my recommendation, I need to contact your advisor. So I need to work with your advisor on this specific problem. And if your advisor refuses, then that's totally fine for me. So we will not do anything further. Okay? So that's it. Oh, by the way, if I recommend your team to for a conference, I will pay for your trip, but one of the teammates needs to be there and present for the paper. So whenever there's a decision to make, you need to let me know, okay, we accept or not. Okay, we accept, but who is gonna mainly focus on the presentation, or who's the main contributor, okay? So the authorship will start with the main contributor, second contributor, and the 2 advisors, or 3 advisors. Okay? So that's what I'm looking for. Okay, that's it. Thank you.